Hi, now I was a little unsure how to do this, so as these are just model answers with the writing in red, I'll just talk a little bit through it as I go through. First of all, you should recognize this as being a normal galvanic cell. That is just a simple battery, not a rechargeable one. So this will have a spontaneous reaction, and the E0 will be greater than 0. Now when it first comes to labeling these electrodes, first of all, they're going to be made out of solid metal, or if there is no solid metal, it would be something like graphite or platinum that you'd be told in the question. So when you're looking at the voltages, first thing to realize is that oxidation is going to be on the left and reduction is going to be on the right in terms of the beakers. Okay, it's a standard way of doing it. And when we look at these voltages, the more positive one is the one that's going to be reduced. So this is the one that goes on the right, so the solid silver goes here, and the iron is what's in solution. Obviously there are negative ions here, but they're not important in this particular case. So on the left side we've got zinc here, and then the zinc ions also in solution. Now in this case you'd normally be told what's in the salt bridge. I haven't put a label there, so I'm going to put one now, and that's potassium nitrate. So as we go down to the question, I've labelled it with the appropriate ions and electrodes. Which way do the electrons flow? Well, they flow from left to right. Now they always go from the anode to the cathode, but you should be able to describe that in a little bit more detail than that, or else you're not going to get much in the way of marks. So from the left beaker to the right beaker, if it's labelled A to B, you just say from A to B, or from the zinc 2+ zinc half cell on the left to through the external wire to the right side. But in all honesty, for most, if it's just a straight question like this, it's just going to be left to right, right to left, A to B, something like that. Now when you're calculating the E0 cell value, just reduction minus oxidation, take care of the negative value, and make sure you do put reduction here, and that you do check that you've got volts down, or else it will be marked down. And I've put a comment in there which was probably a little unnecessary, because it's just asking for the calculator not to necessarily comment on it, but I've said that anyway, that the reaction is spontaneous, electrons will flow freely, and it will produce electrical energy. Okay. Now the overall balanced equation, now for all the way through this whole internal, oxidation always happens at the anode and reduction always happens at the cathode. Now the positive or negative charge associated with an anode or a cathode, that does change, so be careful if you talk about that. But in this particular case we're just talking about doing a balanced equation, so that should be reasonably straightforward. Make sure you include the ions and the actual charge there, don't forget those. Okay, so again this still isn't worth a lot in the way of marks. Sorry about that. Cell diagram notation, again oxidation on the left, reduction on the right. You should have a solid electrode on the outer part, and then you've got the iron here. Okay, and the way that works, remember, is it's reactant, product, reactant, product. Alright, so now and what would you observe in both beakers? Now that really is just observations. Now the actual equation, if you go back to that tells you really everything. This is the anode, so if it's getting oxidized, this solid electrode was going to decrease in mass. These are colourless ions, so you can say that the colourless solution will remain colourless as that forms. The silver ions, which are colourless, form a solid grey silver colour on the cathode. So observations should be reasonably straightforward. Usually on the left hand side you're always decreasing mass as something's oxidized, and you're usually gaining in mass, and those are actually observations too on the right hand side. Okay, discuss the electron movement in the cell with reference to oxidation reduction, relative oxidizing ability, movement of electrons through the cell, and the function of the salt bridge. Now I'm going to go through those one at a time. Now this one is the oxidation reduction processes occurring at the electrodes, and notice in this question it's got the movement of electrons through the cell, so I've kind of done that separately, which is why this first bullet point may not be in as much detail as you might expect. So first of all I'm just making a statement. Anode Zn is oxidized, so always at the anode oxidation takes place. I'm going to say what it's oxidized to, don't leave out that detail. put the exact number of electrons, and while at the cathode reduction occurs as silver ion gains just one electron to form solid silver. So I'm saying what's happening in terms of loss of electrons and gaining of electrons. I'm being specific with a number, and I'm using the terms oxidized and reduced for that one. So that's that bullet point first. I could have used oxidation numbers there, but I've just used loss or gain of electrons. Okay. If it was oxidation number, though, it would be saying it goes from 0 to +2, but I would actually have to say that that's an increase in oxidation number, and therefore it's oxidation. And at the cathode reduction does occur as silver plus goes from having an oxidation number of +1 to 0 in silver, and that's a decrease in oxidation number, and therefore it's a reduction. Anyway, that's bullet point 1. Bullet point 2, relative oxidizing ability. Now this is much easier than you think. This is really just asking you to look at these voltages. So if you look at the voltages that you kind of had at the start of this, you know, how did you actually make a decision on what was going to be reduced? Well, you looked at this one and you thought, well, gosh, that's higher than that number down there, which I forgot to put the negative in, but that's a negative voltage. And because it's a negative voltage, you know, because it is greater, this is the one that's going to be reduced. But I can't say both of these are going to be reduced. It's only going to be the silver ion. That's how you decided it was the one that's going to react. So when I'm describing this, I'm just going to make a comparison between the voltages, say which one is going to be bigger, but then I should use the proper terminology and be specific by identifying silver being the ion that is a stronger oxidant, and it's going to be more easily reduced than zinc. Okay? Therefore, reduction happens to silver at the cathode. Okay? You must name the oxidant, which is just one of the reactants. You don't name both of these. Okay? You don't say Ag plus Ag is the stronger oxidant, because then you're guessing two things, which isn't going to work. Okay? Bullet point 3. Okay, movement of electrons through the cell. So you've got to talk about the process of oxidation reduction and how the electrons actually physically move through the circuit. Remembering, electrons do not move through solutions. They do not move through the electrolyte. Only ions can move in an electrolyte. Okay? So I'm going back to using those terms. As Zn is oxidized, it loses electrons, which is really similar to perhaps to the first bullet point, I know. These electrons move from the anode, so I'm making sure I identify the name of the electrode, through the external wire to the cathode, where silver in the electrolyte accepts the electron to form solid silver on the cathode. Okay, so just describing the process, oxidation reduction, and how it moves. Function of the salt bridge. Okay, that's next. Now when we look at this, now completes the circuit is probably a little over the top, but that is the function of the salt bridge. It maintains charge neutrality. There's an external circuit with the wire, but we consider there to be an internal circuit with the salt bridge which ions move in. So it maintains charge neutrality. I'm just stating the function of it. As Zn forms when Zn is oxidized, so when you're having Zn going to Zn2+, which is on the left side, you're going to get a build-up of positive charge in the left-hand beaker. So because that positive is building up, the nitrate ions, now you've got to be specific with, mentioning the actual ions that are causing this, so the ones that are causing the positive charge to build up, and actually naming the ion that's going to move. Don't just say, the anions move to the anode or cations move to cathode. That's true, but that doesn't show a lot of understanding. And to maintain charge neutrality. On the cathode side, silver ions are used up as they are reduced. Now, effectively, that's a decrease in positive charge. So to get back that positive charge and get it back to neutral, the positive potassium ions will move out of the salt bridge to maintain charge neutrality. Okay? Now, that's the first question.